Hello and welcome to United NDT. My name is Peter Többen. I'm the Managing Director of United NDT in Germany. And today I want to inform you about one of our initiatives to provide training courses for people interested in ultrasonic inspection. Our first course is an easy to understand introduction to ultrasonic inspection and ultrasonic testing. It covers not only the basics, it also highlights the special terminology used in ultrasonics. It explains in theory how an ultrasonic instrument is designed and what happens electronically and physically when ultrasonic testing is performed. Whatever is explained in theory is also demonstrated practically using an ultrasonic instrument. This video covers the first 2 sessions of the course. The full course is available on the Udemy platform. Just go there and search for ultrasonic inspection to find our course. Please click on the subscribe button in case you don't want to miss any new course or any other news provided by United NDT. And now have fun learning ultrasonics the easy way. Welcome again to this online course, Introduction to Ultrasonic Inspection. In session 1 we are going to learn about the principle of ultrasonic inspection. But first of all, some general information about the course. Important notice: whenever you see something written on a yellow background, that information is really important to understand, to keep it in mind when you work in ultrasonic inspection. Expressions in red color are used extensively in ultrasonic inspection, and they are crucial for understanding and using ultrasonic inspection equipment. So make sure that you know the meaning of these expressions. Very important. Whenever you see something in red color, keep it in your mind and make sure you understand what it means. Well, the most effective way of learning ultrasonic inspection, from my point of view, is to focus on the practical exercise. Therefore, the lecture I have implemented something, and I not only explain the theory of ultrasonic inspection, but I also demonstrate the respective features on an ultrasonic instrument. Let's first take a look for the major components of a digital ultrasonic flaw detector. The heart of a ultrasonic flaw detector is a microprocessor. This processor is connected to all other modules and is receiving and sending data and controls the function through various commands. The results will be made visible on the instrument screen. The block diagram on the next page, I will go deeper into that, shows the layout of a flaw detector instrument. One more information: for the practical demonstrations, the standard ultrasonic instrument UT pod from Sonotron NDT is used. This instrument can be remote controlled from a PC and is therefore ideally suited for training courses. The ultrasonic instrument may be operated via the touchscreen. The UT pod is operated by the touchscreen, or from a remote PC over the USB connection. Here's the block diagram of an ultrasonic flaw detector. We see here the microprocessor in the center, more or less, and the microprocessor is somehow connected to the instrument with all the functions here, all the measurements made, and the so-called A-scan display. You will learn about that later. So it will show us the results of any inspection, provided we have done the proper calibration. This microprocessor is connected first of all to a transmitting module. The transmitting module transmits a pulse to the probe. Here there is a probe connection. That means there's a transducer connected to this outlet of the instrument, and that means the transducer will get a pulse from the transmitter, and that pulse, that electrical pulse, will hit a piezoelectric element in the probe. The probe is also called transducer, and that one starts to vibrate. So it means it is producing the mechanical vibration, which is actually then converted into ultrasound waves. You see that here also the processor for the image is connected, providing information related to the image itself, to the A-scan image. And now, as we have seen the transmitter, we also can look for the receiver. There's also a switch here. If it is connected with each other, it is only one transducer connected. You can actually connect two transducers to work with one sending and the other one receiving, but in this case, and that's the usual application, it's actually a shortcut, and that means we have one transducer, one probe only connected. So once the pulse has been sent, there's a waiting time before the next pulse will be sent, and that waiting time is quite long. And within that waiting time, you get response from the sound wave coming out of the material. It comes back to the probe, it hits the piezoelectric crystal, and that one will start to vibrate. And here the transversion from mechanical vibration into electrical pulse will be done. And that electrical pulse will then go up here, go to the receiver, will be digitized, and somehow reach also the microprocessor, and then it will be displayed on the screen. So that's the principle of the block diagram actually of an ultrasonic flaw detector. Now let's take a deeper look into how ultrasonic inspection works. As already explained, we have a transducer, also called probe. The transducer is somehow coupled to a test piece of this size, and there is a piezoelectric element. It's a crystal or some other material, something which can vibrate when it receives the electrical pulse. And that means we are getting a pulse here through that cable to the transducer. It will go towards the piezoelectric crystal or piezoelectric element. That element starts to vibrate, and finally we will have a wave going through the material, hits a reflector. Here we have a crack, for example. It hits the reflector. When the reflector is in parallel to the surface, it will be reflected back. Meanwhile, the piezoelectric crystal became still. Now it hits the crystal starts to vibrate again, and now it's just the opposite thing going on. This vibration will be converted into an electrical signal, and that signal will then go back through that cable to the instrument, and then it can be displayed on the screen. Now, as mentioned already, the pulse which is received here is not a constant pulse as such. It is not constantly transmitted. There's a waiting time between two pulses, and that waiting time is actually also defined by the pulse repetition frequency, the so-called PRF. You see, this is also in red, shown in red color, which actually means this is an important expression to know and to understand the pulse repetition frequency. Okay, just to get a better idea here, we go deeper into that. These pulses are sent with a certain repetition frequency. Once a pulse arrives at the piezoelectric crystal or the element in the transducer, the crystal starts to vibrate, means the electrical energy provided at the piezoelectric crystal is converted into mechanical energy in vibration. In case the transducer is acoustically connected to a test piece using a couplant, this couplant is oil or water, an ultrasonic wave is then created in the material, and this wave propagates through the test piece, as already shown before. Now, coming back and explain a bit about the couplant. Ultrasound is has a high frequency, and that's why we are not able to hear it. The human ear is maximum, when you are young, able to hear something like 20 kilohertz, which is also not very common, but some people can do that. Anyway, ultrasound is much higher. Let's say 2 to 4 megahertz is the standard frequency, which is very often used. And those high frequencies are not traveling through air. It's not possible to travel through air. That's why we cannot hear it, and because the frequency is very high. We need to have something like a couplant. A couplant is a media which is placed between the transducer and the test piece. And that media can be oil, or can be water, air, or other liquids, or grease, or something like that. Whatever is more a liquid media will act as a connector between the transducer and the test object. So then the sound can travel through that layer of couplant,
and then inside the test piece and gets reflected from somewhere. The ultrasonics wave travels with a certain speed. That's also important to understand. This speed, this sound velocity, so-called sound velocity, this is also some expression which is very common and very often used, so you have to understand what it means. The sound velocity is a material constant. And you see also this is in yellow background color, which means important to understand. It's a material constant. What does that mean? For example, if you have an unknown material, you can just measure the sound velocity using an ultrasonic instrument, and then you know what kind of material it is. Because there's a table showing sound velocities for different materials, and you can identify what material it is. It's actually used for that purpose also, the ultrasonic inspections. So in case the sound wave hits a flaw, crack or pore or whatever, like this one, which is parallel to the surface, also important, must be parallel to that surface, the wave will be reflected back to the probe, back to the transducer, and it travels back to the transducer. And this reflected wave is often called an echo. You will also hear that in ultrasonic inspection very often. People are talking about echoes on the screen, for example, echoes coming back out of the material and so on. So that's the reflected wave which has been sent back to the probe and then analyzed and displayed. I also mentioned that this is parallel to the surface. If it is inclined, the wave will hit this piece, but will not be the wave will not be reflected back. It will reflect it in some other direction, like this one, and goes down and here and so on. So will not be evaluated. We will not be able to evaluate the reflection with the transducer. There are other methods to check for cracks which are inclined and so on. We might come back to that later. Now we are coming to see the practical demonstration. We want to show what exactly was shown before. A sound wave travels through a test piece.
This is the equipment we are going to use through the online course. This is the flaw detector. One can see here all the different settings possible, and here the so-called A-scan, where you see actually reflections from the material or signals you get from the probe whatsoever. Now we have a probe over here. This is the ultrasonic probe, a rather tiny one. There are much bigger ones available, but we use this tiny one to have, with a higher frequency, to have rather good signals from this test piece. This test piece is a so-called V2 calibration block. It's used a lot in the for ultrasonic calibrations on steel. This is made of standard steel, carbon steel. And we are using this now for some tests. We want to measure ultrasonically the thickness from one side. So we want to get a reflection from the back wall. This piece is 12.5 millimeter in thickness. Since ultrasonic sound cannot travel through air, we need to couple the probe using some couplant. This is some oil now. I put some oil here on this test piece, and now I connect the probe to the surface, and we see on the screen we get an indication. You see, when I put it down, we get an indication. This indication is coming from the back wall of that test piece. What happens now is that we get an ultrasonic electrical pulse through that cable from the instrument, and here inside this housing there's a piezoelectric crystal, piezoelectric element also called, a bit deeper inside, and when the electrical pulse hits that crystal, it starts to vibrate. So that means the electrical energy is transferred into mechanical energy. That type of vibration is then causing the ultrasonic wave, which runs through from the surface of the element to the surface of the probe of this transducer. It's also called transducer. Probe and transducer is the same meaning. And then when I couple it, it runs through the material, and I get a reflection from the back wall. And now I can measure it using this tool here. This is a so-called monitor gate. It actually analyzes any signal, the high signal in that so-called monitor gate, and then measures the distance from 0 to the peak of the signal. And we see here it measures SA, that means the sound pass in gate A, this is called gate A, is 12 millimeter. Now we know that this one is 12.5 millimeter, but we measured 12, so that's something wrong. The calibration is not yet correct, so we will see how we can correct this in the following videos.
So welcome to session 2, the basics of ultrasonic inspection. First we need to explain a bit more about certain terms used: pulse repetition frequency, PRF, and sound velocity. We actually talked about this already in the first session, but let's talk about it a bit more to have a better understanding. So the pulse repetition frequency and sound velocity is explained over here. The PRF stands for the number of pulses sent in 1 second. So suppose the PRF, the pulse repetition frequency, is set to 500 Hz on the instrument, on the ultrasonic instrument. It means that per second we have 500 pulses sent to the transducer, to the probe. Transducer and probe is the same meaning. The time between two subsequent pulses is calculated as 1 divided by 500. 1 second divided by 500 is 0.002 second. So I have here shown how the pulses look like and what the waiting time between those pulses is. So we have from one pulse, let's say the maximum peak on the first pulse to the next one, the transmitted pulse to the next one is 0.002 seconds, provided we have set it to 500 MHz, which is a quite common value. It's even higher in most of the cases. And what you see here, by the way, the type of pulse, how it goes up, high, a high amplitude, and a low amplitude, and it goes up again, but not the same height as you see. That means there is a certain damping. The pulse is not going for a long time. There's a damping material behind the piezoelectric element, which damps the pulse after receiving the first electrical pulse. So it's a rather short time, it comes down and reaches almost the zero line. And then we have a long waiting time between those pulses, and that's important, this waiting time, before we send the next one. So in case the test piece is made out of steel, the sound travels with a sound velocity of 5,920 meters per second. You see, it's also in red color, means important to remember. The sound velocity in steel is 5,920 meters per second. So it's very fast. This value is a constant for the sound velocity of steel. It's a constant. Sound velocity is in general a constant for the material, as we have learned before. In 0.002 seconds, the sound wave is traveled 5,920 meters per second multiplied with 0.002 seconds. 11 is 11.84 meters. It's quite a long time in this short, a long way in this short time, 11.84 meters. Which means when the PRF of 500 Hz is selected and then we inspect steel, there's a rather long waiting time before the next pulse is transmitted. And within this waiting time over here, we can get some reflections from flaws which might come back to the transducer. Then reach the piezoelectrical crystal in the transducer, causing the conversion from mechanical energy, vibration, into electrical energy pulse, and finally this creates a signal on the screen. Alright, I think that makes it clear how things are working. We are sending pulses with a certain pulse repetition frequency, and there's a long waiting time between two pulses, and within that time we receive from the material reflections and so on, and that type of signals we receive can be analyzed and then shown on the screen. Now we explain a bit about the so-called A-scan, a very important expression also. This is an A-scan over here. This is called the A-scan. And actually the axis, the x-axis, stands for the time or also the distance, depending on the way you calibrate the unit. Actually we want to calibrate in the distance, not in the time. And the y axis is here it's the amplitude height. It's actually the intensity of the echo of the signal received from any reflection. Alright, a signal we receive from the transducer, actually a reflection from the material which then is converted into a signal received, will be amplified or weakened depending on the settings on the instrument. And then it will be digitized and finally displayed on the screen. Now what we see here is the typical display on an instrument screen. This display is called the A-scan. On the left it shows the transmitting pulse. Here, transmitted pulse. That one is shown, which is generated by the instrument and then sent to the transducer. With a certain number of pulses, the display will be updated. For example, 50 times per second means 50 Hertz update rate on the screen. So that means the digital screens will be updated with a certain frequency, similar to a TV screen or something. And for the human eye, you can actually not see the updated signals at all. It looks like a stable signal, more or less, on the screen. When the ultrasonic wave propagates through the test piece, that means here it propagates through the test piece, it gets reflected at the back wall here and runs back to the probe, where the piezoelectric element converts the vibration into electrical energy, a voltage. And this voltage causes then the amplitude shown on the screen, on this A-scan. If properly calibrated, the signal comes at a distance equivalent to the thickness of the piece. In this case, you see we have a certain length of the test piece, and the amplitude which is shown here on the A-scan has the maximum amplitude exactly at the end of the test piece. Means here we have properly calibrated everything, and when we analyze the signal here, the distance after proper calibration, we will measure exactly this distance. This is important to understand, because it actually means that you can measure any thickness from one side. Suppose you have a pipe and you don't know the thickness of that pipe. How to know the thickness of that pipe? You have only access to one side. And with this ultrasonic inspection, you have just to put a transducer on. Of course, you have to calibrate it properly, the instrument properly, and then measure the thickness of the pipe from one side. That's an important feature, and very often used in ultrasonic thickness gauges also. Let's look on the A-scan again. So we see that the signal comes exactly here at the end of the material. But now, one thing is important also to understand is the ultrasonic wave actually has traveled to the back wall, got reflected, and was running through and back. Actually, it has done the traveling through that test piece twice. But here we have the signal over here only, and it looks like we are measuring only one time movement through the test piece. But that's not true. The instrument automatically divides the time which is spent to travel through by 2. This is automatically done in order to do easy measurement of the thickness straight away. So I hope this has been clear. Now we will do some practical demonstration again. A transducer will be placed on a V2 calibration block, and we will see the A-scan display again on the instrument itself. A bit about the V2 calibration block. In the ultrasonic inspection, there are 2 major calibration blocks used, the V1 and the V2. And when you hear about that, you just should know, okay, they are existing, you can do certain things with it. We are not going deeply into the calibration blocks in this course, but in the other courses it's of course very, very important when you go for level 1 or level 2 training course.
So as said, I will now go and connect the instrument to the computer. So I have here a cable and I connect it here. And now what I have is I run everything, that means the software, from the computer itself, and we get that image here, and I put it down on the video, and you will see much better what is happening here. Alright, I connect again, and let's a bit explain about A-scan, what A-scan means. So we have again used the V2 block. We put the probe on, we get some signal. What I can do is I can freeze the signal now, so lift up the probe and it remains, the signal remains here on the screen. Now let's have a closer look to the so-called A-scan. This is the A-scan, and within that A-scan we see some signal over here, which is actually the so-called initial pulse, the transmitted pulse from the electronics to the piezoelectric element in the probe. That causes this kind of signals over here. And after that it comes to a stop, the vibration stops, we have a certain waiting time, and after that waiting time we get this signal which comes from the back wall, and then we can measure it. That was quite clear so far. What we see here, this axis, the x-axis, is actually either the time axis, or you can also calibrate it so that it is at the depth axis. Now we have calibrated in such a way that it gives us indications in millimeters. So it's the distance, means the distance from the surface of the material, that it would be the right thing, from the material surface to the reflector is measured. So this axis is the distance. Now the other axis, the epsilon axis, is the axis for the amplitude height, the height of the amplitude, which is somehow giving us an idea about the size of the reflector. Now it's a back wall which is reflecting, so it's a huge one, it's a huge reflector, and that's usually comes to very high amplitude. But we have the chance just to manipulate that. For example, this is called the gain. We can manipulate that by, I need to connect the probe again. Manipulate that using here those arrow keys, increasing the so-called dB. This is the unit for the gain, the dB. It's not a linear relationship here. It's a logarithmic one. That's why it is dB. Anyway, I can increase, and I increase everything on the screen, of course, or I can decrease over here. The increment I can use here, you see it's now 1 dB, so every time I click here it's 1 dB less or 1 dB more. Means I can analyze the sensitivity, let's say, and amplitude height, the gain of a certain reflector, using also those kind of settings. Yeah, that's the A-scan. If you like what you have seen, please give us a thumbs up and subscribe by clicking on the United NDT logo, and go for the complete course under udemy.com, searching for ultrasonic inspection. Thank you.